Ignition sequence start. 6, 5, 4, 3, 2, 1, 0.
Hello and welcome to Ignition Sequence. I'm your host, John Murphy, and today we pick up our second conversation in a series about the evolution of Earth's atmosphere and climate dating back 4.6 billion years. We'll take a fascinating journey through time, back to the origins of life on Earth, where tiny microorganisms played a pivotal role in forming the early atmosphere and shaping the planet into the world that we live and know today. Our guest is Dr. Minik Rosing, a world-renowned geologist whose research has radically changed what we understand about life's early forms and the development of our atmosphere. Minik's discoveries reveal how early microorganisms harness sunlight to transform Earth's atmosphere, laying the foundation to life as we know it. His research sheds light not only on the origins of life and the evolution of the planet, but also offers critical insights into the delicate balance of Earth's climate system. Minik, wonderful to meet you and to talk to you. I'm in Los Angeles, but you're in a whole different part of the world. Where are you right now?
I'm on the southeast coast of Australia. I'm here because we have some scientific research going on with agriculture in Australia, where we're trying to improve the yields and take out carbon from the atmosphere. But that's a whole different story. So
we'll have to have you back on the podcast, to talk about that. I'm really excited to talk to you because I've never met or spoken with anyone from Greenland before. How many people live in Greenland or are from Greenland?
56,000 people in all of Greenland. So Greenland is, the biggest island in the world. It's an enormous country, and there's 56,000 people spread on that enormous country. But it's a wonderful place. Everybody should take an opportunity to go there because it is really a fantastic place.
I found this very interesting because I didn't know this either, that Greenland is, it has autonomy, but it's not a self-sovereign nation. It's part of the Kingdom of Denmark.
It's part of the kingdom. It's not in that sense, but it has what's called self-government. So so what happens in Greenland in terms of internal affairs and resource, all this kind of stuff is governed from Greenland. So Greenland is a very special nation. It's the only, I think, nation where the indigenous population actually has the political power.
Wow, that's fantastic. And I think it's pretty interesting too that Greenland is geopolitically aligned with Europe, but Greenland is actually part of North America.
Yeah, exactly. So it's a stepping stone. And, when the North Atlantic Ocean formed and America and Europe started drifting apart, they were together for billions of years, and then they decided to go each their way. And Greenland first followed Europe for a while. That's the Labrador Sea. It opened. Then it changed its mind, and the Atlantic Ocean jumped on the other side of Greenland, and Greenland followed North America to the west, and Europe drifted to the east. So there's always been a bit of ambiguity.
And it's really funny because when you look at Google Earth and you see Greenland and you see Iceland, I'm a little perplexed because Iceland is green and Greenland is ice. It's just very, very unique and strange place.
I think we have to say Iceland is small and Greenland is big, so it seems like it's a lot of ice, but actually around the ice there's land that is much more green than Iceland is green. So people who came there 1,000 years ago to Greenland from Iceland, they thought that it was extremely green. Which I think this thing about not knowing people live there. I once had many years ago a strange conversation with an astronaut who had been to the moon, and when he heard I was from Greenland, he said, "Greenland? Can you go there?" I thought that was very funny.
That's hilarious. So what was it like growing up in Greenland?
Wonderful. To me, Greenland, that is kind of paradise lost. It is, when I was a kid, I grew up in a small settlement with only 7 or 8 people, and we could do whatever we liked, and there was absolutely just do whatever came to mind. So, and Greenland is people often think of the Arctic as extremely dramatic and full of dangers and all kind of stuff. But to me, it's extremely peaceful and uneventful, and what makes it so wonderful is that if an event happens, it's usually one you made yourself. So that's really nice.
And I guess growing up as an adventurous young boy with obviously a scientific mind that was developing, what a vast playground to let your mind expand and to be curious about your natural environment.
absolutely, because you are sitting there in the midst of everything, and wherever you look, something is interesting. And there are, even if Greenland in the Arctic, of course, biodiversity is not anything like at lower latitudes, but there's still all kind of curious animals and plants, and so I think it's really, it's really inspirational place.
And what pulls you into the field of geology? What kind of lit your fuse about studying geology and getting your PhD in that?
Part of it was calculated, a part of it was curiosity. I think curiosity was the first part, that when walking around in Greenland as a kid, and you start to realize that the rocks are different, they all are different, and there must be some reason why they're different. There must be some story hidden in them. This one part. The other is, of course, you realize they consist of minerals, and these minerals are intriguing in their own right. The calculated part came after I finished high school and had to start a university study. I think geology was because I realized that it's a job where actually your work is to go out and go for a walk out in the mountains and look at interesting stuff. I thought this couldn't be any better. You get your salary from just doing what you like the most.
Well, I saw one of your videos preparing for this interview, and you made a joke. In fact, it was a presentation at a club. It was called Science and Cocktails.
Oh yeah,
and, yeah. And you made a joke. You showed a slide of scientist people all in their their white lab coats and their gloves and their goggles in a lab doing mundane work. And you're going, see that scientist there? That's a boring job. My job is much more exciting, to be outside and walking around the world.
Exactly, and that is the truth. Of course, geology has a lot of high tech and very advanced scientific tools, but you cannot do anything in geology without being out in the real world and looking at the real rocks. And so I think that it really is. It's one of these types of science that's not necessarily hypothesis driven. It's driven by observation. And I think that when you teach people what science is in high school or whatever, you always say this thing about you having a hypothesis and you go and blah, 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 which is to some extent true. But a lot of science is also just going out and being amazed and being completely overwhelmed by the richness of the world that surrounds you, and then try to describe it in the best possible terms you can. So I think that's more what geology is like.
Well, let's get into the meat of what this podcast is all about. We're talking about early Earth, the development of Earth as a planet, a living planet, the bloom of life, and the beginning of our atmosphere as we know it today. And it's a continuation of a podcast we did earlier. Do you know Mark Harrison from UCLA?
Oh, yeah, of course. Yeah.
He says hi. Anyway, but we talked to Mark, and we talked about his book, the Hadean. How do you say it? Hadean or Hadean?
Hadean.
Yeah.
Hadean.
We kind of debated that a little bit, but talk about all the
Hades, which is basically hell.
Yes, correct, right, and I understand that. And he explained that to us, but we talked about all the eons, actually about his book, the Hadean Eon that he wrote.
Yeah.
But can you tell us about the four big eons and what they mean and represent as far as the formation of this planet and life?
Yeah, of course. The eons are the major divisions of Earth's history, and as we just said, the Hadean is. I think it's a little bit of a misnomer because we actually know very little about it. That's the definition of it, is that we have no rocks that can tell the story about the Hadean. So we have to infer from other observation what the Hadean was like. Then after that, we have the Archean, which is a period of time that. When it was defined, it was more kind of the part of Earth's history where we had no certain sign of life, and there were kind of everything was. It's a very small part of Earth's rock inventory that is from the Archean. After that, you go into the Proterozoic, and that is where you start having a world where you can see traces of life everywhere in the rock record, more or less. And after that, you go into the Phanerozoic, which is kind of the modern times. That's when animals and plants and all these things that I think most people think that Earth is a planet that has an atmosphere, an ocean, it has plants, it has animals, it has all these things. And many people think of life as plants and animals and not microbes necessarily. So I think the Phanerozoic is where the Earth shifted from being a microbial world to being a plant and animal kind of world. And I think even when people think about very far, deep geologic time, they'll think about dinosaurs or something like that, which is true a geologist. That is in the absolute most present part of the geologic history.
Yeah.
So the part that I work in, which is we call it also the Archean, that is kind of the border between the Archean, the first where we have rock record, and into the Hadean.
Mm-hmm.
That is so far back in time that it's almost impossible to imagine. 3.8 billion years ago, 3.8, no person can count to 3.8 billion in a lifetime. If you count day and night for your whole life, you wouldn't get, maybe reach a billion or something. So
wow,
it is absolutely unbelievably a long time ago. And if you look at the universe is 13.7 or something like that billion years old. So the rock record on Earth goes about 3.84 billion years back in time. So that's pretty much, that's a quarter of all time that existed in the universe are memorized by the rock record in Greenland first and foremost.
Yeah, and I would like to propose. I think we're moving into a different eon right now. I think we're I think we're moving into the Eon. And where life is going to be just become an avatar, an AI generated avatar of yourself. But that's just another podcast. You have a very kind of radical idea in theory that life in our atmosphere, which we breathe, which is, the source of life and everything else in life itself, and the photosynthesis process started a lot sooner than has been understood by geological science over the decades. Is that correct?
Yeah. That is correct. I think that it is a field that has developed for a long period of time. I think actually the whole idea of understanding the atmosphere, again, I think that it's not so long ago that we thought that Earth was kind of a package deal that was granted by God or something else, so and Earth is what an Earth is like. It has an ocean and atmosphere and so forth. And in the mid 1800s, people realized that actually climate on Earth was dynamic. They discovered the traces of the ice ages, which showed that the Earth have had changing climates and so forth. And that made them start thinking about, but what is then the atmosphere? Because the atmosphere is what controls the temperature on Earth. They had realized that quite early. So people started wondering about what is the composition of the atmosphere, how did it evolve, and so forth. But I think it is quite interesting that it's only about 150 years ago that people even started wondering about that Earth has a history and that the atmosphere and the oceans have been changing over time. So then the next step was, of course, realizing that the oxygen in the atmosphere is a product of photosynthesis. That is, some organisms that made the oxygen. And we can see that oxygen didn't come into the atmosphere until about 2.5 billion years ago at any extent. And that was seen as a kind of, this would be taken as an onset of photosynthesis. But of course, people also start to see that there are processes going on in the Earth's environment where organisms have been able to influence the composition of the ocean and the atmosphere in one way or another. And maybe the photosynthesis would have been earlier on Earth, but it just was not able to basically overwhelm the processes that consumed oxygen as fast as it was being produced. Mm-hmm. I think my idea came from a slightly different point of view, and that is going into what is the fundamental purpose of photosynthesis. Why did life invent photosynthesis? And that is because if life didn't do photosynthesis, it would have to live on this tiny little amount of chemical energy. Chemical energy, that's what in a battery, for instance. It's something that you can drive processes by tapping energy from some chemical processes. If you look at the whole Earth, the amount of chemical energy produced is incredibly small. It is almost ridiculous. My point of view was, okay, if life was living from just the chemical-free energy coming out of Earth's machinery itself, then it would not be able to make its presence known because it couldn't do anything that would not have happened anyway, basically. It's like if you find a flat battery somewhere and you know that there was some energy at one point in time, but it would still be the same kind of energy. What I started looking at was, when did life start to manifest itself by changing its environment and changing the composition of the atmosphere and the ocean? And when we can start trace that, we can see that actually it was able to do that right back to the earliest part of the rock record, which is 3.8 billion years ago. Life was able to influence its environment. And the reason why this means photosynthesis is that the only other source of energy in our system, that is the sun, photo, that's the light.
Yes.
And if you cannot convert light to chemical energy, which is photosynthesis, then you can't do anything. And the interesting stuff is that sunlight, there's a lot of energy coming from the sun. It's 10,000 times more than or maybe even more than that, than energy that is running the whole Earth's machinery. But this energy cannot be used for anything. It's just converted to heat, and then it's radiated back into space. And that is because the energy in the solar radiation comes as single photons, little energy packages. And each individual energy package is too little to do any work, basically. You can heat up what it hits, and then it'll cool off again, and nothing has happened. But photosynthesis, what is the fantastic invention made by microorganisms early on, is that they could make a system that could store up energy from several photons until they could afford to break the bond between hydrogen and oxygen and water, and then do some work with that. To me, it is not so much looking for any particular specific remnants of these organisms or of the process they did, but just simply say that if they can impact the environment, they are able to harvest the light from the sun and use it for a purpose.
And talking about photosynthesis, which you did say is, light energy being converted into chemical energy. I think most people who reference and understand that think of big plants and trees and green fields and things like that. That was not the case 3.7 billion years ago. You're talking about microorganisms, correct?
Absolutely. I think that everything points towards something that would be like what we call cyanobacteria, blue-green algae nowadays, which are not actually algae but bacteria. And they probably were the inventors of photosynthesis. And if you look at plants have these chloroplasts, which are little organelles inside the plant cells that do the photosynthesis. Those chloroplasts are actually not the plant itself. They're actually, you could say, it's called an endosymbiont. That's something that is doing some symbiosis within the organism. So they are actually just kind of embedded small cyanobacterial remnants that are sitting there and doing all the hard work while the plant sits and look beautiful. And we all go look at the flowers. They're beautiful and fantastic. But it's actually tiny little bacterial remnants that are sitting inside every cell of the plant that is running the machinery.
And as a scientist, to prove, some of your ideas, you actually have to have some physical evidence. So what rocks are you looking at? Now, in our last podcast, Dr. Mark Harrison was talking about zircons in rocks and things like that. Is that what you're looking at as well, or are you looking at something different?
I was working many, many years ago in these oldest sediments we have on Earth, which are in Greenland, a place called Isoa, and they're about 3.7 to 3.8 billion years old. And actually, we know the age of them from the zircons that Mark was talking about, or similar studies. But anyway, we have these rocks, and you can imagine a rock that's been on Earth's surface for almost 4 billion years have experienced one or two things. And so they're quite contorted and disrupted and deformed and metamorphosed, all kinds of terrible things that happen. Mm-hmm. But even inside it's this rock complex, you can find tiny little domains that have escaped better than the rest. And in some of those, you could actually find well-preserved layers of what was once sediments. And you can see clearly they were deposited in the ocean. And there's one thing that is really interesting already there. As said before, we oftentimes take a lot of these things for granted, but actually just knowing that there was an ocean, we didn't know that until we found these rocks. So that's one thing. So we had an ocean, but then the next thing was we found that these rocks were full of little particles of carbon, of basically just the element carbon in the form of graphite, which is like pencil lead that you write with. Anyway, that's already very curious because carbon does not exist in its free form on Earth because the planet Earth has a lot of the element oxygen, not air oxygen, but the element oxygen. So everything on Earth is oxides, basically, except the core, which is way, way, way into 2,700 kilometers inside the Earth.
Man.
But everything in the outer part of Earth consists of oxides, including the carbon. It's carbon dioxide in the atmosphere or limestone in the rocks or whatever. So if you have free carbon, there must be some reason for it. And that reason on Earth is almost exclusively life.
Fun.
So, okay. But then so we found this carbon, and that is in its own right, that's very, very kind of mysterious and interesting, because life was not expected to exist on Earth at that point in Earth's history. But then the nice thing about life is that life, when it builds organic matter, when it builds its own organism, it distinguishes between the two stable isotopes of carbon. There are carbon have two isotopes, carbon 12 and 13. And they take up carbon-12 more readily than carbon-13. So an organism has a deficit in one isotope relative to the atmosphere or the ocean where it grew up. And God damn it, I mean, if not those little carbon particles had an isotopic composition exactly like you could go and take, your little net from your aquarium down to the beach and scoop up some goo from the ocean, put it into a mass spectrometer, you get the same number out. So this shows to me, of course, clearly this was derived from life. But what is more important is also that Earth is incredibly, you could say, conservative. These organisms are doing the same thing over and over and over again to 4 billion years. So the photosynthetic apparatus was invented one time in Earth's history, and everybody who used it just copied the previous one. So it's not, and it works well enough that there's no reason to change it. So I think it is absolutely fascinating.
Yeah.
How many generations of organisms have lived in 4 billion years? It's quite a few.
Well, it's almost like the question, we know about the Big Bang and the theory of the Big Bang and how just the universe even started. But I think it's quite a kind of a leap is, how does life begin on this planet? As you mentioned, I believe there has to be a combination of hydrogen and water and carbon. And how does it get attraction? This is a big ball in the space. How does it get enough traction to start creating and building an atmosphere? Because that's your theory, is that these microorganisms started through the tiniest little beginnings of photosynthesis, creating the atmosphere.
Yeah, and not only did they create the atmosphere, but also they kind of built in a thermostat regulator, because in the period of time since these rocks formed till now, the luminosity of the sun has changed dramatically. So the climate should have had a short interval of time where life could exist on Earth, where it's neither frozen nor overheated. Like if you look at Venus today, it's 500 degrees centigrade, and because it's overheated, and you look at Mars, it's deep frozen because but Earth actually was able to maintain through that whole long period of time as a livable place. So these organisms not only kind of inadvertently made an atmosphere, they also controlled the composition of the atmosphere to suit their purpose, basically. Of course, it didn't do that in a willful way, but the system just has some resilience in it that basically regulates the atmosphere. So it works for life.
I was going to ask you, do you feel that Earth's position around the sun, its unique position at exactly 93 million miles away from the sun, is it because of its exact position that we didn't get too hot or get too cold?
I don't think so. I think that there's definitely a zone where it was possible, but I think I think Venus could probably have had life and maintain life. Maybe they had life, but life never came up with a photosynthesis solution. To me, the key thing is, if you have photosynthesis, you have plenty of energy to do the maintenance of the atmospheric composition, because you can just tap the sun energy to do it. If you don't have that, you are a victim of circumstance. You can't control your destiny. But I think back to your question about how did then life emerge, and I think it is even the simplest organism we have ever seen and we can ever imagine is so complex that to me is one of these questions that I can't see how we could ever come up with. We come up with parts of solution to some of it, but it's still still too complex. I think Svante Arrhenius, who was a very famous Swedish chemist who came up with all kind of fantastic things, among others, greenhouse effect in 1896. But he had the solution. He said that life is a universal imperative. So that's it. If conditions are such that life can exist, life will emerge, because it's the way the system works. We don't ask, why is it the electron spin, or why is it that
Right.
there are many things. They're just the way it is. And I feel kind of a little bit compelled to just follow Arrhenius and say, well, it's here, it happens. That's the way it's meant to be.
This new theory of yours, or with you and other partners developing this, how has that challenged the scientific community, and how has it kind of turned over the tables a little bit?
I think that it's always with every idea you come up with in science. Of course, there will be, which is the whole nature of science. It will be discussions, and some will say this is a really stupid idea, and some will say this is a brilliant idea. And of course, the truth is always, you hope, somewhere in between those 2 points. But I think the big problem with these whole Earth system ideas is that, first of all, you cannot test them by experiments. Obviously, you can't make another Earth and see how it would develop. And geologic evidence is, I see, very, very strong, but it's also very difficult to quantify in a way so you can present it unbiased. You make an observation with your eyes and your brain and whatever. You see something, and as we all know, what you see is actually not only what your eyes see, it's also what your brains add to the story. So it's very difficult to have an objective observation that then you subjectively write it down in a paper and try to explain what you saw. And I think that's the main source of of frustration in geo-based sciences, is that it's so incredibly difficult to relate observation. And there, in one bit of information, you will often have a scale from micrometers to 100 kilometers kind of observations pulled into one statement. So I think that is. I think that this idea we proposed that basically that photosynthesis was the origin of or created the basis for forming continents on Earth. I think that it was very, very hardly contested in the beginning, and I think it is much less so now. And I think that most people would agree that it might not be completely correct, but it's definitely not completely wrong either. But when we submitted the manuscript, we had 2 reviewers. That was hilarious. One said that this manuscript borders on heresy and must not be published. And The other one said, if this is published, it would destroy forever the reputation of the authors. And the miracle happened that the editor of the journal said, if it evokes so strong emotional reactions, we will have to publish it. We need to get it out there so people can get furious or whatever.
So you wrote this paper with other scientists participating, of course, that photosynthesis is basically the beginning and the source of all life on the planet and our atmosphere. What was the old theory, so people can understand the differences? What has been the traditional old theory about how the Earth became full of humans and plants and life and atmosphere?
Yeah, I mean, of course, they not that old actually, but you just go a couple of hundred years back in time, and there would be definitely a strong belief that it was all just delivered as a package solution, and everything that's here now was always here. And so, but I think in the understanding of the development, Darwin, of course, with his evolutionary work, that was focused only on plants and animals. And Darwin himself had an enormous problem in getting past the Phanerozoic into the earlier part of Earth's record, because there you had no fossils, so you didn't have any progenitors of all these. So you had like a big bang of life in the Darwinian world, in that suddenly there were all kinds of animals on Earth, starting from the first layer where you found any fossil at all. You found many different ones. So the whole idea that there should be one one progenitor for everything else that they had evolved from, was difficult for him to understand. He said that himself. But then, of course, it was discovered that the reason why was because we had the microbial world, that basically where evolution took place. I'm not sure I would say that photosynthesis has always been there, but it's definitely the driver for the proliferation of life and it has been there as far back as we can see, and we cannot see any further back, so therefore it's difficult, of course, to address the question, because we have no evidence basically.
You're from Greenland, and Greenland, as you said at the top of our podcast, is a magical place, one of the most magical, beautiful places on Earth. And the Arctic is just almost like a Garden of Eden to you, Tell us about the rocks, because so much history and knowledge and understanding of where our planet began, its evolution, and where we're headed are in the rocks. What can you tell us that's unique about the rocks in Greenland and how it can inform where the world is headed?
I think what's really special about Greenland, and the reason why Greenland has been delivering a lot of knowledge about how the planet works and how the history of our Earth is, and the reason why we've been able to find these extremely small fragments of very, very ancient rocks in Greenland, is that Greenland has enjoyed an ice age much longer than anywhere else on Earth. Basically, it's kind of just getting out of the ice age, and that means that you have the Greenland ice sheet, which has over the past 10,000 years or so retreated from the rocks. So in Greenland, despite my claim that Greenland is very green, actually has a lot of rocks that is not covered by plants and other disgusting things. So you actually have well-polished, fresh rocks, and the climate is Arctic, so they don't weather very rapidly, the rocks. So if you live in California, if you go to the highest areas, you see all the rocks are nice and clean and barren and so forth. You go further down into the valleys, and they get more and more weathered and falling apart and crumbling and so forth, because warm weather basically eats up the rocks and cold weather preserves them. So in Greenland, you have rocks that are accessible. You can see the geology. And that is why we find so many interesting things, in my view. There's no part of Earth's history that's not covered by a rock in Greenland. So basically, you can find examples of everything, and that means that it is kind of a big showcase of what Earth really is. And if you want to learn about Earth, I would claim you have to go to Greenland. That's the only place you can ever understand Earth.
I love that. And you talked about, Greenland is the last spot on Earth to kind of recover from the last ice age. How many ice ages do we know or theorize have happened here on the planet in the 4 eons that have taken place?
Well, I think ice ages, in the current understanding, of course, are those glacial periods on Earth. But I think that we definitely know that there has been at least 3 or 4. There has been way back in Earth history, in the Proterozoic Eon, there has been a ice age. Then at the tail end of we have these global ice events, the snowball Earth events, of which there have been 2 events where the whole Earth was basically covered by ice. We know that because we find in Greenland, of course, where else we find rocks that were at that time living on the equator, but are covered by moraine, and you can see that there was ice, glaciers basically at sea level at the equator on Earth about up to 700 million years ago or something like that.
So you're saying you could find Greenland rocks at the Earth's equator.
Yeah, they're now in Greenland, but when they formed, Greenland was at the equator. So Greenland,
okay.
So the continents are drifting. So at that period of time, Greenland was sitting right on the equator, and still there was ice that basically deposited all the glacial products that we know from glaciated areas. And then, of course, we have after the warm period in the earlier part of the Tertiary, where we descended into the current ice age period, where we have all these glaciations. And I think when in more kind of colloquial terms, I think people think of an ice age as one of these glaciation events. Whereas if you take the whole period of a number of million years, we have had many periods where there's been warmer and colder and warmer and colder repeatedly. and that cycle is driven by the Earth orbital, the Earth's spin and orientation and many other things. But I think there's been at least 3 major ice age events affecting the planet, and we don't know how we got in and out of the earlier ones. We have some idea of what has controlled climate in the most recent period.
One of the things I found very interesting in watching one of your presentations online is the fact that when mankind discovered fire, that was the end game. That was the start of the carbon problem that we face in the planet. Just that first spark of fire, putting carbon into the air, and it was game over.
No, but I think because that fire changed our physiology, changed everything. We started cooking food, and we did all kinds, and that of course gave us that advantage that made us, start taking over the whole the whole business here. No, but it's interesting. I find that absolutely fascinating. That it's those tiny little things that happen, like the photosynthesis evolved in one little organism, and it survived and came, and then just took over the atmosphere. But what really is fascinating in relation to fire is in mid 1700s, there was somebody realized that heat is an expression of energy. Before that, we thought heat was a material; it was a matter that was contained in something else. And the reason why we thought that is you compress some air, it gets warmer. So it's like if you have a sponge full of water, if you press it, it gets wetter. So it was we thought that heat was kind of a substance. But then when people realized that heat is energy, and you can translate energy from one to another, as soon as this little idea came, somebody realized, okay, so that means I can convert heat to work. So I can be on the sofa while heat does the work for me. Mm-hmm. And when that happened, that was the exponential increase in human impact on Earth, was we realized. And now every human on Earth have about 25 human powers or something from fossil energy, or now, luckily, increasingly from solar and other renewable sources. But still, I think the problem for us is not that we realized all these wonderful things, but the way we sourced the energy turned out to be a bad idea in retrospect. But at the time, it was a brilliant idea to just throw some coal into a machine and let it do all the work, and you can do wonderful, fun things in the meantime.
What is this ISIS or ISIS sediment? And what is unique?
Isua sediment, yeah.
Isua. Oh, maybe I need glasses. I thought it was an S. I'm sorry. Isua sediment.
Isua sediment. Isua sediments, they are tiny. Now they're solid rocks because they have been compressed and heated in Earth's interior on several occasions. But they still preserve very fine laminations. That was like if you go and look at marine sediments today at the bottom of the ocean. The sediments settle by about 1 millimeter per 1,000 years or so, very, very slow. But a little bit of clay comes out with the rivers, gets suspended in the water, drifts about, and then suddenly sinks into the bottom of the ocean and builds up these very, very fine laminated sediments. And that's what we find there. Then we can also see at times there have been maybe some tectonic earthquake or something happen. So we have little avalanches of mud that have been rolling out also. We have that today on the ocean floor again. So you get little sandy layers. And we can see that these sandy layers were from a mud avalanche because they're more coarse-grained in the bottom and get finer upwards, which is like, it's like you shake sediment in a bottle and let it settle. So basically it's something that was a avalanche kind of. So if you look at a rock like that, again, it cannot get over how exciting it is. You can see this layer, maybe this thick, that formed during a period of, say, 2 minutes, 3.8 billion years ago, and you can still see the structure and everything preserved in that layer from that mud avalanche. So, and that we can walk around and see and understand something that took place like this so long ago And again, it shows you, like before we said, that we can see that life has been extremely conservative. But Earth itself is an extremely boring planet. Can you imagine a rock sitting there looking the same for 3.8 billion years and nothing happens? I mean, it is absolutely desperately boring place. So when we try to narrate geological things, we always talk about these forces of nature and whatever. The forces of nature are ridiculously small. What makes geology work is time. We have so enormous lengths of time that even very, very small forces can actually cause an effect if just they have a long enough time to work. So I think but it's those moments where you see this and you say, this cannot be true. You can actually see this happen during a period of, say, a minute or two, and you can still see the product sitting there, just looking the same.
So those photos that you see in science magazines or in the news or on videos where you're looking at the Greenland ice sheet melting and you flowing into a river or an ocean, and you see this like thick little barrier, that's the Isua sediment you're talking about.
Yeah, that could be. Yeah. That's yeah.
And it has some particulates in it from billions of years ago.
Yeah.
That's amazing.
Yeah.
That's really incredible. Speaking about the Greenland ice sheet, I know it's receding. Is there any accumulation going on at all, or is it just completely in receding?
There's accumulation every year, but the following summer melt off is larger than the accumulation for most of the ice sheet. Some of the ice sheet is still above. It's the top of the ice sheet is more than 3,000 meters altitude. So it has until I think it's last year where it actually rained on the top of the ice sheet, which never happened before ever. But other than that, it's always below freezing because it's so high up. So they'll still accumulate a little bit there. And since the ice flows as a plastic medium out towards the coast, that's where the melting happens when it goes down to lower altitudes. But the melting now is something like 500 cubic kilometers of ice melting in a summer, which is a completely incomprehensible amount of water, and that's of course ending up in the ocean and contributing to sea level rise.
And how's the health of the Arctic and the Antarctic?
I think the Arctic and the Antarctic, of course, are very different in the sense that, first of all, the Arctic, the North Polar region, is an ocean. And the ice on that is there is just sea ice, a thin layer of sea ice. Whereas Antarctic, the South Polar region is land covered by an ice sheet, which is very thick. So that's the main difference. So there's much more water stored in the Antarctic ice sheet than there is in the Arctic ice sheet, because the ice sheet is actually only the Greenland little in that context, relatively small piece of the Arctic region that has an ice sheet.
Is more of the Arctic being revealed now because it's melting?
It's not. I wouldn't say it's not very, very significant. It's more that the thickness of the ice is shrinking than the extent. Of course, you can see valley glaciers and all this along the margin. They are melting back. That's really very conspicuous. But if you look at the total area covered, I don't think it's that much change. It's mostly that it gets thinner because of the melting, and as it melts out at the edge, just more come flowing out plastically. So it's kind of self-regulating a little bit the extent. And also when it gets warmer, the climate gets warmer, the ice moves faster. So therefore it can compensate for what's falling off at the edge. There'll just be more coming from behind, basically, for foreseeable future.
One of the things that you're very passionate about is educating everyday people around the world. People like me, I'm science curious, but I'm not science credentialed. I don't know nearly as much as you do about all this, but informing people through art installations to get them almost hands-on to what's happening to our climate and its effects on the ice sheets. And one of the things that you've done are these glacial ice exhibits, like in London, and you go around and just big chunks of glacial ice that you just put in a nice circle or semicircle, and they're just propped up there that people can just walk up to and see and touch and smell and put their hands on. And how is that working? And is it moving the needle? Are people becoming more and more aware and starting to see tactical results?
Yeah, I think all these things collectively move the needle. I think the needle has moved. I think you have to look more and more desperate around to find somebody who really denies that there's a problem. But I think on the other hand, I think that the purpose that Olafur Eliasson and I did those Ice Watch projects was not only to cause concern and make people think about this, but also to make people have a different view on what it is, why we have to protect this. And it's not only because it might end up as water in our basement or in our backyard or something. It's also because ice in its own right and the glaciers and the ice sheets are wonderful, and we cannot afford to lose these things. So I think it was as much to make people realize that this is not a block of frozen water. It's like a living entity. It is a fantastic, strange thing with beautiful. That has, as you say, it whispers to you because all little compressed air bubbles, they crack and water runs off. You can take a breath of the air. It's actually the atmosphere as it should be with 280 ppm CO2. Because the air was caught 10,000 years ago or something like that.
I know that's what blows me away. You can see the little air bubbles inside these little ice streams, and that's an air bubble from 20,000 years ago.
Yeah, exactly. This is the air.
And it's crazy.
It is crazy, and that's why they are magic, and that's what we try to say. They're beautiful. They're absolutely, grown men would start weeping when they see them. So they are absolutely wonderful. But they are also, I think, they are poetic, but they have evidence of stuff that we can tap the air out of them and find out what the atmosphere was like, and all these fantastic things. So I think it is. So it was as much that aspect of it was we cannot afford to lose something with that fantastic beauty and poetic value to mankind, to humankind.
But I think the most important thing is you're making science emotional, not intellectual.
Yeah.
And that's how you pierce the heart of people, is to make it emotional.
Totally agree. I don't think anybody, that's what marks us from the animals, is that we don't learn from experience, and two, we don't act on facts. We actually have to have an emotional driver for deciding to do something. Then we can use our intellect to make it impossible for us to do these things. But we don't do them for rational reasons. We actually need to be emotionally inspired to do something. I think inspiration is a wonderful word. It's kind of, you get blown some fresh air into yourself.
Speaking of ice sheets, because as you mentioned, the Arctic is actually over water, so we're talking about land mass and ice sheets. How are the two different, and what does it mean with them, shrinking or not necessarily accumulating?
Yeah, I think clearly there are two things. One is when they're shrinking, the water that melts off the ice sheets or drops off as icebergs end up in the ocean and basically contribute to the increase in the ocean sea level that we are observing globally. But I think that for the Arctic, there's something really interesting also, which may have some serious implications for Earth's climate. And that is that the ocean currents, which are basically the conveyor belts that take some of the excess heat from the tropics and bring it up north to, say, northern Europe and other places, and make sure that the heat that is deposited from the sun on Earth is spread more evenly. That's done by ocean currents that transport the heat around. But the main transport system is fed by formation of cold dense water up in the Arctic near Greenland, where in the winter, when you form sea ice on the Arctic Ocean, you freeze the fresh water and you get more salty and denser and colder water that sinks down and start running down on either side of Greenland and form these currents. And the loss of water through these currents is what pulls up the Gulf Stream up north, because you need to compensate for the water that disappeared, run as kind of a deep submarine current. So anyway, all these current systems would be dependent on having this formation of this very salty, dense water. And as you put fresh water into the ocean, you might actually start slowing down this system. So I think that there are two aspects of the melting where, for the Arctic, the main concern is, of course, to some extent, the water that you put into the ocean and raise the sea level. But the other is also that it could cause a collapse of the climate as we know it today, because the distribution of heat and cold will be different. And everybody have, made their life kind of based on the assumption that climate is what climate is. But when climate changes, all your assumptions may prove wrong, and you are not prepared to live in the climate you are moving into. So I think that is probably where one of the more serious concerns is about the Arctic part, is that it has such a deep impact on the whole global climate system.
Wow, that's pretty astounding to think about.
That's good just before bedtime to think a little bit about that.
For sure. Oh my gosh. How long does it take? Like, say an iceberg chunk breaks off and starts, drifting out into the open ocean. How long does it take for an iceberg to actually melt completely away?
It depends, of course, on many things, but usually it doesn't. If it goes out into the open, to the North Atlantic or the Labrador Sea or wherever Titanic met its iceberg, that was probably what was left of a much larger one, and it'll take a few months usually, and it'll be gone. So I think some of the large icebergs that break off the ice shelves in Antarctica, they can linger for a much longer time and make very long journeys because they are so enormously massive. But most of the ice that comes off the Greenland ice sheet does melt quite rapidly, and the North Atlantic water is warm enough that it can. Actually, it turns out that a lot of the retreat of the glaciers in Greenland, those are what we call marine terminating, that reach the ocean, is more that you have warm ocean water coming in, melting the glacier, than it is kind of surface melting of the glacier from the warmer air. It's the warming of the ocean that is causing the most of the retreat.
Wow. And it's causing there's so many ripple effects, just the warming of the ocean. Species are dying off or being affected. Entire species are like, I think it's just very bizarre that now you see pods of killer whales now in South Africa. It's just kind of weird, And in my lifetime, I'd never heard of them. Now the great white sharks are missing from South Africa because all the killer whales. And it's just, it's like it's dominoes, falling dominoes. There's all kinds of ripple effects.
That's the whole thing about climate. There's no good or bad climate in that sense, but there's a rapid change basically mess up the system because everybody have what do you say? They have organized their life and the way to sustain themselves, assuming that this is the conditions. And when this change, everything, the whole system start to crumble. I think that is, I think this idea, I think every culture, because humans have lived through ice ages on Earth, every culture have looked back at the period up towards their own time as an improvement in climate because it caused such a wonderful thing as themselves, whereas those who were there before, of course, to them it would be terrible what happened. So retrospectively, climate always gets better, but of course, those who are there when the change happened, to them it is catastrophic.
Studying ancient glacial rocks in Greenland, what have you learned about our climate system, and what's your big takeaway, and where we're headed, and what knowledge have you gained that can maybe help us slow things down or to alter its direction, if at all?
I think there's one very important thing we can see, and we have already touched upon that is that we have had a condition on Earth that has been conducive for life for 4 billion years that we have been able to maintain, even with large kind of ice age events and whatever here and there. But we have been in a habitable zone in all this period of time. And I think that is because we have those thermostat systems. And one of these thermostat systems has to do with the maintenance of the carbon dioxide in the atmosphere it's maintained by the weathering. That is basically that the carbonic acid, that is CO2, that is dissolved in water, that reacts with the rocks and forms something else and binds to CO2. So we have CO2 coming out of volcanoes and rotting away organic matter, whatever. CO2 is being taken up by reaction with rocks. We know that has been maintaining part of the Earth system over a long period of time. And we can use this knowledge to basically say, okay, our main problem now is that we have too much CO2 in the atmosphere. Can we take that out again? Yes, we can. We can do it by enhance this weathering process. And this is what's called now enhanced rock weathering, that people are looking at. And it turns out that the two factors control the weathering, the rate, how fast weathering takes place, how efficient it is taking CO2 out of the atmosphere. That is temperature. The warmer, the more efficient it is. And the other is how much surface of minerals is exposed to the air. And there's where Greenland, of course, comes back again as a wonder place, because the ice in Greenland mills the rocks underneath it into a very, very fine powder. Fine powders have enormous surface areas. Greenland is very cold, so the fine powder sits in Greenland, do nothing. But if we take it from Greenland to warmer places like Australia, where I am now, then you bring it to a warmer climate, and it has the surface areas for free made by the ice, and start reacting as fast as it can to take CO2 out of the atmosphere. So we actually have understanding the past is really important to be able to come up with meaningful solutions to current problems. And there's a very famous principle that we always use in geology, which is the present is a key to the past. We can understand the past by understanding processes that happen today. But we could also say that the past is the key to our future. Because if we understand the past, we know how the Earth system responds to various perturbations. And because we are so strong as that we are, because we have all this energy and we know how to harness energy, we can also, of course, we have the strength to actually do meaningful things to change the system back to probably not to where it came from, but to something that will be. I still think that with goodwill and good understanding, we can make a wonderful future for ourselves.
Did I hear you correctly saying that if you took some of the soil sediment that's underneath the ice sheet from Greenland and put it in Australia or somewhere in Africa, it could start absorbing the carbon there and decrease the carbon levels in those areas?
Yes, and will be then in the global system. Yes, it absolutely does so.
Wow.
The ice sheet is 3,000 meters thick. It's enormously heavy, so it crushes the rocks to a powder where each particle is about 2 micrometers. So if you take 1 gram of this rock flour, the surface area that can react is 200,000 square centimeters. Whereas, if it just had it as a rock, it would have a surface area of 3 square centimeters. So it's 70,000 times faster reaction than if it was just the rock surface that you had exposed. And it's just sitting there in the Arctic doing nothing. You take it to a warmer place and puff, it goes off and start taking CO2 out of the atmosphere. So we better start doing that.
Wow. I think Greenland's going to be pretty busy in the next century. It's going to be the top country in the world. It's going to have economic growth and expansion.
We have started seeing the Arctic as kind of the victim of climate change, as a place with no agency or so forth. And therefore, I think it would be really fun when Greenland is actually at least a part of the solution to all of this, rather than just a victim of it.
That's fantastic. I mean, that's really exciting to hear. That's really exciting. One thing that we talked with Dr. Mark Harrison on our last podcast was about tectonic plates, and the Earth's crust and the shifting and the movement and it's all that. How can that affect our climate situation, and is it something that we can latch onto or utilize in some way?
I think it can help us understand something. I don't think we can utilize it because these are very, very slow processes. But what we see, of course, is that the continent reflects more solar radiation than the ocean does. So if all the continents, they will have a period of time where they were kind of forming a girdle around the equatorial region, that would have changed the Earth's climate to some extent, because you reflect more of the sunlight instead of turning it into heat. And so these processes, we do understand how it works, but whether we can kind of, it's very difficult to see how we could stimulate the system to do what it hasn't already decided to do. If we decide to move the trajectory of movement of North America, it's difficult for me to see how we would do it. So, but the understanding help us understand how the system responds. And I think most important is that what we can see is that the Earth system has a lot of stability, but we can also see that it can change due to relatively modest changes in some of the factors that control the system. So it's not beyond human capacity to actually change some of these things if we really feel that we need to. And of course, there's been a lot of talk about radiation, solar radiation management as a way of controlling Earth's climate. And I think there's rightfully a lot of concern about how will we do that without causing problems that might be greater than those we try to solve. But still, we actually our knowledge tells us that it is not beyond our capacity to change the Earth system if that's what we decide is necessary.
Do you think the tectonic movements of 3-4 billion years ago are radically different than what's happening today? Are they faster or slower, or is there any difference at all?
Probably maybe a little bit faster. I don't think they were much different. I think if you go before 4 billion years, I don't think that there were large continents on Earth at all, maybe none at all. So there would have been different, but you'll still have subduction, I think, of ocean floor like you have in the present Earth. That's the best way of cooling the system, the inner part of Earth, is by taking cold stuff down and warm stuff up. So I can't see how you could avoid that. But I think when I first came to Isua, these very old rocks in Greenland, and I think you go to the oldest rocks on Earth and you think, okay, I'll see something really exciting, something that I haven't seen before, something that looks peculiar. You go and look at it, and it looks exactly like any other rock you've seen anywhere. And that is, again, I think, again, it testifies to the conservative nature of our planet and the boring. It couldn't even come up with a different way of doing stuff.
Hey, Earth is boring, but it's been here for 4.6 billion years, so it must be doing something right.
Exactly. Yeah.
Exactly. Let's talk about, we've mentioned Mars, we've talked about Venus, Earth is right between them. Looking at those two planets and studying ancient rocks and Greenland rocks, what can we learn, if anything, about our celestial cousins?
I think we can learn a lot, both about Earth from those, and we can learn about them from us, because they are made in the same system. Obviously, they were made in the same sequence of events. They are made from more or less the same material, and we can also see that the planet-driven processes are kind of similar. The surface of Mars is basalt mostly. The surface of Venus is basalt, as far as we know. The surface of the Moon is basaltic material almost exclusively. So all these processes have to do with the cooling of the inner planet. That is what determines the starting point for crust formation on any planet. We can also see, of course, that climates can go wrong. Neither Mars lost its atmosphere. Venus got an atmosphere of sulfuric acid and too hot for anything to live there, and so forth. So there has to be some serendipity for a planet to end up like Earth. And again, my point would be that we were lucky enough that some organism discovered photosynthesis and were able to basically take control of the system. So I think what we can learn maybe is that the planets without a controller, they would run through kind of a predictable physical chemical trajectory that depends on the luminosity of the star and the cooling of the planet itself and so forth. And if you have a more, stochastic process like evolution, where it doesn't follow a trajectory to be part of the planetary system, then you will not follow that slavishly, that trajectory that I think would be determined just by physics. So I think it's more deterministic without life.
Has there been any evidence of photosynthesis on Mars that's been spoken about or written about?
No, I don't think there has been, and I think that, of course, if I don't think there's any active photosynthesis because the atmosphere on Mars doesn't show any indications of it, and I think that in that case, what we would to rely on would be to get some samples back from Mars where we can look at what is in the geologic record on Mars. That's of course one of the missions, the current rover mission, is to collect samples that at some point in time can return to Earth so we can get a closer look at them.
As a geologist, when you look at these stunning photos and videos taken from Mars today, you can look at a new picture every single day.
Yeah.
From a geologist perspective, when you look at the surface of Mars and you even listen to its atmosphere with the recording, what do you think? Do you think that photosynthesis tried to happen and didn't take, or do you think it did happen and we got lost somehow?
I that's one of these things where I would say I would have no idea where I would start to form an argument either way, because Mars is so much smaller and it's quite different from Earth. It also has the mixture of component in Mars is a little bit, tiny bit different from Earth. So I mean, if we follow the argument from Arrhenius and that we subscribe to some extent, that if life conditions are present and life should emerge, you would think that then Mars, we know there was liquid water on Mars, there was the sunlight, there was a substrate of rocks and so forth, so it should happen. And maybe it just never got enough, strong enough lever to control the atmosphere on Mars. I think
if you were given the opportunity to go there and study it, would you do it?
Nope, I wouldn't, because then I couldn't spend my time going to Greenland, which would be much more fun.
Obviously, I can tell that you love your job. You love what you do.
Yes.
And it's your passion, and that's a beautiful thing. It's not a job because it's your passion. So what words of advice would you give to young science-minded kids about, if they're science-minded and curious and want to pursue things, getting into these fields and enjoying not only fulfilling their own spirit and soul, but contributing to the world to make it a better place?
Yeah, I would definitely start with one word that you used, and that's curiosity. Look at the world with curiosity. Don't try to be blasé about anything, and also allow yourself to be excited about stuff. I really think that's important, to allow yourself to be excited about things, even though other people think that they are very, 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 very pedestrian and boring or whatever. And I think the other thing is that I think that don't try to plan a trajectory for your life or career, but be optimistic, not in a bad sense, but if some opportunity presents itself, go for it and see. It might be a thundering fiasco, and then go for the next one. It might be great, but don't think that you can plan what I'll do this and this and this and this and this. And also, to some extent, I don't think it matters what topic you choose. What matters is that you invest enough time to be good at it. If you're good at something, it's fun regardless of what it is called, the topic, I would say. And if you do something out of curiosity and devotion and everything else, you will certainly be useful relative to problems we have. And one of the problems is, of course, that we don't have enough good stories in the world. Good stories are what drives humankind. So if you just, study something and turn it into a very good story, at least you have done something that is fundamentally good for all of us, I think.
As a scientist and studying where we are today and realizing that the Earth has survived 4.6 billion years of turmoil, ups and downs, ice ages, are you confident? Are you neutral? Or are you a little worried about the future of the planet?
I'm confident. I'm worried about us not basically
paying attention to the warning signs.
Yeah, exactly. But I mean, our skill and our ability and our everything else is what brought us here. And if we use the same skill and ability and so forth, we can also get back on dry land again. Absolutely. So I think that the worst thing that can happen is that we surrender to completely, giving up. We can't afford that. So no, I absolutely. We just, and I think, again, we should not do it out of dread or anything. We should do it because there's stuff that we really like to preserve. That is the world that we live in. And we should just not forget to enjoy it while we do it. I think work done joyfully is more efficient than work done out of some as a chore.
And if you want to take the vacation of a lifetime and see Earth, what it looked like at its very earliest stages of its 4.6 billion years of existence, go to Greenland.
Absolutely. And even if you don't want to see that, go to Greenland anyway, because you'll come back a better human.
Photosynthesis, to you, my takeaway from what you just said is that photosynthesis is kind of like the magic bullet of the entire planet, that just sparked life, continues to propel life. Is there a way for us to generate photosynthetic behavior in our natural world to improve our carbon situation and to extend the life of the planet?
I think that there are, in some ways, something that has the same purpose. That is this, what they call direct air capture, where you use solar energy to make electricity that you use to run some chemical process. But I think that, to me, the elegant way to doing it is basically to stimulate the photosynthesis that's already there. There's the amount of activity, particularly in the ocean, that is happening in life is actually. What controls the rate is the input of mineral nutrients from the continents into the ocean and also into soils if you look at plants. So I think the best way would be to stimulate the growth of photosynthetic organisms, both in the ocean and on land. And we know how to do that. And where can we go and get the material? We go to Greenland and take that rock flour that we have made from the glaciers, because that releases nutrients for plants and microbes to perform photosynthesis. So we can absolutely do that. Agriculture is a stimulation of photosynthesis that we've been doing for 10,000 years. We know how to do that kind of stuff.
And does the Greenland ice sheet make this rock flour that you're talking about?
Exactly. That is manufactured by the ice sheet. It's just sitting there. It costs nothing to manufacture it. It's naturally occurring, and it just needs a shovel and a bucket and somebody to take it somewhere else where it can stimulate some plants or some organisms in the ocean.
So you're saying some kids, some teenager, go up and do some hiking in Greenland, stick a shovel in the ground and get rock flour?
Yeah.
Wow.
But of course, remember, Greenland is a sovereign nation, and it is, of course, a resource that is like all other natural resources everywhere on Earth are regulated by laws and whatever. But in principle, yeah. But
wow.
I think it will happen. It will happen.
Minik, it's been wonderful having you on our Ignition Sequence podcast. Thank you for giving us your time and your stories. And we will absolutely have you on again. There's too much left to talk about.
Absolutely. And it was a real pleasure talking to you. And thanks for a fun conversation. So see you another time. And here's a magpie blending in.
Ignition Sequence is produced by Accelerator Media, a nonprofit organization dedicated to inspiring a lifelong pursuit of knowledge. The podcast is made possible in part by viewers and listeners like you. If you'd like to support our work and help us continue bringing Ignition Sequence and other programs to a global audience, please visit acceleratormedia.org and click the donation button. Your contribution helps fuel our mission to ignite curiosity and empower future world changers. Listen, learn, repeat.